Alright guys, welcome to chapter 2, and we're going to begin with some notation, and it's really specific and picky notation, so just bear with me while we get this notation going and then we'll work some homework problems with it. Now with this, the reason for this notation and why we have to do this is we need to classify different things, and we need some symbols in order to be able to do that. Just looking here at some quadrilaterals, we have some different ways and different shapes that make quadrilaterals, and they're defined either as rectangles or trapezoids or parallelograms, that sort of thing. So that's another classification that's going to go along with this set theory. Alright, I have 3 sets listed here for you. I have set A, B, and C, and they're defined in a particular way. You'll notice there are curly Q brackets around each, and the elements are listed out for you. So there are 4 elements in set A. There are 2 elements in set B. Set B happens to be a subset of set A because all of the elements in B are also in A. And set C has 4 elements as well. I could say that M is an element of C. I could say that B, because M is an element contained in C, I could say that B is a subset of set A. I could say that 3 is not an element of B if there are the same number of elements in each. I could say that set A is equivalent to set C because they have a one-to-one correspondence between the elements. We will go through the different ways to describe a set. Sometimes it's easier to use words. Sometimes we can just make a list. That was what I did in the previous slide, was I just made a list of the elements in the set. And sometimes we can use set builder notation, and that would be where if you were talking about all the numbers greater than 0, you might write x greater than 0, and that would be a form of set builder notation. So in the PowerPoint here, they've given us a list of words or different ways to describe our set. So we have, words, and then we have just the plain old list written out. The natural numbers, because I want them to continue, I could use just the ... and that tells me that that list is infinite. So the set of natural numbers, those ones that we naturally start counting, that set is an infinite set, and I can write that as a list. Going again with the whole numbers, and that just is the natural numbers plus 0, I could say that with words, or I could write out a list. Looking at the set of integers, and this is our definition for integers here, now we could just write that out as a list as well, showing that it goes in both directions. Alright, in using this particular set builder notation to look at the rational numbers, it is overwhelming at first, I know. When I write this A over B, what I'm saying is, well, let's just start at the very beginning. So Q is my rational numbers, and that is the symbol that we use for the set of rational numbers. Q equals, and then I use curly Q brackets to denote that it's a set. So it's the rational numbers is the set of all A over B. That straight line down means such that. So this straight line down actually means something to me, and every time I see that straight line down, I think such that in my head. Such that A is an element of the integers, and b is an element of the integers. Sometimes you will see integers represented with a capital Z and not an I. I'm not really quite sure why they used an I here, but Z is widely used. And so it's each one of those is an integer where b is not equal to 0. So that would be like a 1 over a 2. They're both integers and b is not 0, so that's a rational number. 4 over 2 is a rational number. Those numbers that aren't rational would be those square roots of prime, pi, and e, in case you're wondering what wouldn't be rational. In your homework, you're going to look at the different ways to describe these sets, and first up, the set of letters and the word elementary. So how would I describe that? It would be this guy right here. This one is a set of sets of numbers, and I mean letters actually, a set of sets. So this set contains 1, 2, 3, 4, 5, 6, 7, 8 sets. This one is a really whacked one. 8 sets where each of those 8 sets has one element. That definitely wouldn't be it. I can list them off. That's not true. The set of all x such that x is one of these letters. That works, but that's not really how this is supposed. This should be some sort of notation talking about sets of numbers. This doesn't work because this is actually a set with one element, and that element is the word elementary. And you might have it would look, maybe you'll understand it better. Let's say brother. All right, so this is a set containing 3 elements, so you can see that this is a set containing 1 element, but we want the set to contain 1, 2, 3, 4, 5, 6, 7, 8 elements, and you are not to double up, so you wouldn't list those e's twice. The next one, because they wanted me to do a list here, set builder notation. This one would be it, even though I really don't like it, but it would be my set builder notation. I briefly discussed the infinite set of the natural numbers, the integers. A finite set is one that can be counted, or in other words, is a whole number. The set of whole numbers is an infinite set. The set of integers is infinite, real numbers, and so forth. In this next slide, you will see 3 different ways to describe the positive even numbers. There's a verbal or word description, and then there is the list description, which is very straightforward. The set builder notation is a little awkward at first, but let's look at what it says. The set builder notation says the set of all x such that x is 2 times any one of your natural numbers. So if I start where my n is an element of my natural number, so if I start counting, if n is 1, 2 times 1 is 2, it's sitting right there. If n is 2, 2 times 2 is 4, it's sitting right there. So there is the set builder notation, and that collects them all. Next, you'll see the symbol for a subset. You can use 2 different symbols actually for subset. We have just a regular subset, which is this symbol here, and that just means that every member in one set is also a member in the other set that you're talking about. There's also a proper subset. Now, proper subset is one in which one set is a subset of the other, but not the 2 sets aren't equal. So it's a more specific symbol. But either one, if it's just a regular subset, you can use either symbol. All right, we're going to make us pizza here, and we need to figure out how many different subsets we can have. So, and that would be how many different kinds of pizzas. So we're going to list this out, how many subsets I could have. let's just say a plain onion as one of my subsets. I could have onion, sausage. I'm going to list these out for you. Alright, there's the whole list. Oh, and I forgot about one. I could also have what is referred to as the empty set, because I could just have none of those toppings on my pizza. So there are all these different subsets of this one set, and these are the different ways different combinations I could have for my pizza. So be sure and note that guy right there, because that's an important one. The empty set is a subset of every set. Alright, I fixed my thing there. Alright, the empty set is a set, or sometimes it's referred to as the null set. It is a subset of every set. Sometimes we'll use this symbol here. It's a O with a slash through it, and I like to use the bracketing guys. Sometimes people refer to this as zero, especially computer guys, so I usually refrain from that. They're also wanting you to know that every set is a subset of himself, so you could have a pizza with everything on it. That's what that would mean. And then, of course, the pizza with nothing on it, you can think of the empty set as a subset of every set that way. I spoke a little bit about equivalent sets. We can, down here at the bottom, these last two sets each have 3 elements in them. They are called equivalent sets just because there's a one-to-one correspondence, and you use that little curly Q guy to designate that. If they're equal, it means they're exactly equal. Doesn't matter what order everything is in, just as long as they contain exactly the same number of elements and those elements are the same. Now remember that this is very notational. This top one would not be true because 6 is an element. He is not a set. I could have said, well, they're getting ready to say that, so never mind, I won't have to do that. 6 is an element of that set there, so that one would look like this one. Now this next one would be this right here. If it's a curly Q bracket, then we can say that this is an element, and it's an element, it is a set, and it is a set containing the element 6, and it is a subset of that other set. So those curly Q brackets denote that we're talking about a set. Now C is kind of interesting because this right here is a set of sets. So on C you're looking at the set 4 is a member of this set. So you would say that this set containing the element 4 is an element of this bigger set because there is a set in there containing the element 4. I know it's really picky. Now I'm going to conclude this video on set theory, and I will discuss Venn diagrams in the next video.